Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 34, fundamental concepts of dosage calculations, part 2, one-compartment pharmacokinetic model. Today's objectives are to describe the operational principles of the one-compartment pharmacokinetic model, define the concepts of drug volume of distribution and clearance, and learn how to calculate their values from plasma drug concentrations, and learn how to determine the relative distribution of a drug in the plasma and tissue from its volume of distribution. Now, pharmacokinetic models are used to calculate specific dosages from quantitative estimates of the ADME pharmacokinetic parameters. A pharmacokinetic compartment is an imaginary unit that consists of a group of tissues that display similar rates of drug distribution. Okay, this is important. In the one-compartment model, all tissues are lumped together in one compartment and they are indistinguishable from each other. Now, the central circulation is always at equilibrium with all tissues, and the concentration of a drug in the plasma is some multiple of the drug concentration in the tissues. So what I'm referring over here is that drug in the plasma, I would just write it as Cp, and it's not equal with drug concentration in the tissues, but it is some multiple, okay? So this is what we're referring. These two, obviously, fluids are at equilibrium, but their concentrations do not have to be equal. Now, it's important for us to know that the one-compartment model is commonly used in the clinic to adjust dosages, okay? So this is a schematic that describes the one-compartment model. As you can see here, the central circulation with the plasma drug concentration written as Cp is always at equilibrium with the tissues, and the drug concentration is written as Ct. Now, this distribution is considered to be instantaneous. No delay. In a split of a second. This is the condition for the one-compartment model. Also, very important, one-compartment pharmacokinetic model is considered to be a first-order pharmacokinetics, so first-order kinetics. So all the equations that we've learned in the previous lessons referring to first-order kinetics are applicable over here, and they are gonna be used to calculate dosages. Drug elimination is taking place from the central compartment and is also first order. Everything is first order in a one compartment model, okay? All right, so the essential features of the one compartment model is that drug distribution is essentially instantaneous, and drug elimination is a first order process characterized by a first order rate constant. As I mentioned, everything all kinetics of the one compartment model are first order kinetics. Of course, the equation that is central to first order kinetics is equation 12.6, which says, and of course we're referring to plasma here, so that's Cp. One thing that we need to remember is that we determine plasma drug concentration all the time. We never measure the concentration of drug in tissues. We measure drug concentration of drug in plasma. So we draw blood from the patient and we determine plasma drug concentration, and then we derive equations that we can calculate therapeutic doses. So pharmacokinetics is all about plasma drug concentrations. Okay. Now this is the first order rate elimination constant, and as we're going to see in a minute, this is related to the volume of distribution, which is called Vd, and the drug clearance, Cl. Okay? Now, you remember, of course, this equation, which is the common fundamental equation for the concentration being equal to mass over volume, and we have seen this equation over and over again, especially when we describe the principle of mass preservation. Now, the way we determine mathematically volume of distribution is essentially the same equation, but now we change the symbols of the parameters. So the volume of distribution of a drug is equal to the amount of drug in the body. So AB is the amount of drug in the body, not in the blood, over the concentration of the drug in the plasma, okay? What you need to know is that if you choose to determine the VD from AB over CP, make sure that you determine the amount of drug in the body exactly the same time that you determine the concentration of the drug in the plasma. Why? So what could be the problem of, let's say, determining the amount of drug in the body 5 minutes after the dose administration, but the plasma drug concentration was determined 2 hours after the drug administration? Well, within 2 hours, a lot of processes could take place that they could have eliminated or metabolized or distributed the drug in the tissues, right? That's why. So again, if you use this equation here, make sure that you determine the amount of drug in the body exactly the same time as you determine the drug plasma concentration. Now, the VD can also be determined by dividing the IV bolus dose, and remember that this is a direct administration of all the drug in the plasma, in the central circulation, instantly, right? Over the concentration of the drug in the plasma at time 0. So this is C0, and we're very familiar with this term. Now again, the concentrations here are referring to plasma. Okay, so simple as that. I think we have mentioned everything here, all the bullet points, and of course, special emphasis on the mass preservation equation, which is essentially equation 13.2. Remember, the mass here is either the AB or the IV dose. That's the dose in milligrams anyway, right? And the concentration of the drug in the system is either CP or C0, okay? And the volume of the system in this case is the VD. So basically, the mass of the drug would be equal to C times V, right? And this would be the concentration in the plasma, and this would be the volume of the drug. That would be the VD, for example. The volume of the drug in the body, or the volume of distribution of the drug. Okay. What's important, very, very important for us, is to know that VD is a dose-independent parameter that depends on the physical-chemical properties of the drug and the disease state of the patient. However, if we are dosing regular patients, then obviously the volume of distribution is a dose-independent parameter characteristic of a drug, that you can use it for every patient out there to determine average doses. So this is why it's very important, regardless of dose. Okay, VD is always and it's only dependent on the drug. Now, obviously, from the equation, the relationship here, if the volume of distribution of a drug is small, then the CP after administering a single IV bolus will be large, okay? Drugs with a low VD exhibit a relatively small distribution of the drug to surrounding tissues, effectively lowering the tissue drug concentration and, of course, effectively increasing the plasma drug concentration. We all understand that, right? So if the VD is low, that means the CP is high, right? And the CT, of course, must be low. Drugs that are extensively distributed to surrounding tissues are characterized with large VDs and high CTs, concentration in the tissue, and low CP. So obviously here, you may use the value of VD to gain information about the properties of a drug. So a drug that has a large VD must be very hydrophobic, okay? All right, good. So dosage increase results in proportional increase of the CP and the CT. We know that. Okay. Now the way to calculate the fraction of the drug in the plasma is using equation 13.3. And that can be done by dividing the patient's plasma volume by the drug's VD, as you can see there. Now, what we need to remember here is that for a 70 kilogram patient, right, for a regular weight patient, the volume of plasma is equal to 3 liters. Okay, let's see how we can do that. So in example 13.3, we have administered an IV bolus of a new drug, 60 milligrams is that, right, to a 70 kilogram adult male, and therefore this individual has a VP equal to 3 liters. And resulted in a serum concentration at 0 time. So this must be C0. And that was 1.5 milligrams per DL. So that is basically 15 milligrams per liter. DL is 0.1 liter. Okay. Calculate the volume of distribution of the new drug. So we're going to start, since we have the IV bolus, I'm going to use this equation here. VD is equal to IV dose over the C0. The IV dose is 60 milligrams. Make sure you convert the units appropriately, okay? So 60 milligrams over 15 milligrams per liter. And 60 over 15, that's 4 liters. Where is the drug mostly located? So now you're going to get actually a fractional percentage, right? So I'm just going to write the fraction of the drug in the plasma. So I'm just going to write plasma here is equal to VP over VD. And that's equal to 3 liters over 4 liters. And that's equal to 0.75 or 75%. This is amazing, right? Okay, so this is what we have just described. You may read it at home later. Now, in reality though, in real practice, determining the volume of distribution of a drug is not as easy as is implied in example 13.3. So basically what I'm saying here in all these bullet points is that nobody can determine C0. You understand that by the time you inject the IV bolus, it's already 1 minute anyway. So how would you determine the concentration of the drug at 0 time? You can do that by measuring CP at multiple time periods and then use the first order equations. Care feed your data by linear regression or non-linear regression analysis and recover or determine the VD and the first order rate elimination constant from your best fit equation. Let's see how we can do that. So here we have administered a 450 milligram dose IV. The weight of the patient is 70 kilograms. Blood was drawn at predetermined time intervals, and drug concentration of each sample was determined as shown in the table. So you have drawn blood after 1 hour, 2, 3, 4, all the way up to 10 hours, and you determine the plasma drug concentration as is shown there. Care fit the data and determine the apparent volume of distribution of this drug. Okay, so what we have done here, I've plotted the raw data, not the ln. And now we know that the equation is CO is equal to C is equal to C0 e to the minus KT. What I've done over there, I've care fitted the data non-linearly using regression analysis. And what you see there, the C0 is directly given to me. That's the C0, and of course that's a K. Compare it with this equation there, okay? And you're gonna see it. So that's the advantage of if you know how to care fit non-linearly your data, you can get the C0 and the K directly from the best fit equation. And the care fit you can see from the correlation factor is almost 1. That's almost perfect, okay? Now, if you're not comfortable with non-linear regression analysis and you're gonna plot the logarithmic linear form, that's fine too. So you convert the concentrations into ln concentrations, plot them, and you get a line. And now be careful, the slope is gonna be K, okay? So that would be your K. And the intercept is gonna be the ln C0. And of course, to determine C0 would be e to the, let's say, 1.5284. Either method is okay, perfectly okay, and you get the same number anyway, okay? All right, now from the C0, once you determine the C0 and you have the dose, you can use the equation VD is equal to IV dose, right, over C0 and determine the VD. As simple as that. Now, in the future lectures, you're going to learn another way to determine the VD from K and clearance. But at this point, we can only determine it using C0 and IV dose. So this is what we have done here. C0 is 4.612 milligrams per liter, or if you use the best fit equation, same number, and K is 0.461 per hour. Now the VD is equal to the IV dose, which is 450 milligrams over the C0 or the CP0 here. It's 97.6 liter. Now CP0 is the same as C0, okay? They are all concentrations in the plasma. So the VD is 97.6 liters, and that denotes a relatively hydrophobic drug, okay? You can verify this by determining the fraction of the drug in the plasma using the VP. So remember, FP is going to be fraction of the drug in the plasma is VP over VD. So if VP is 3 liters and now this is about 100, right? So only about 3% of it is in the plasma, 97% of it is in tissues. Now here, what I have described is if you don't have a trend line, so you don't have a best fit equation, you could approximate C0 from the intercept graphically, but be very cautious, make sure that your approximation is accurate as possible, okay? And of course, K can be calculated from the slope of a line. Again, it's going to be an approximation, and remember, so I'm just going to write it here, your slope in this case is going to be ln C0 minus ln C1, ln C2 minus ln C1 over T2 minus T1. It's not going to be C2 minus C1. So just one remark here, you cannot determine the slope of this graph, okay? We are referring to the slope of this graph here, which is a line. The slope here is different anyway, everywhere, okay? So this is meaningless for the slope. If you want to determine the slope of the logarithmic plot, remember to take ln C2 minus ln C1 over T2 minus T1, okay? Now let's move to our final pharmacokinetic parameter, perhaps more important than VD or equally important, drug clearance. So clearance is defined as the volume of plasma cleared of drug per unit time and has units of volume per time. This is a very unique definition here. And actually it takes few months to get familiar with it. It is a parameter that measures the efficiency with which the kidney and liver can extract or eliminate the drug from the plasma. So essentially clearance doesn't tell you whether the drug is metabolized or excreted. It is defined as the volume of plasma cleared, regardless of mechanism of drug per unit time, okay? That's what it is. So it relates the rate of drug elimination from an organ, okay, with the concentration of the drug in the plasma that enters the organ. So as you can see, mathematically, equation 13.5, clearance is the rate of drug elimination over the plasma drug concentration. Okay, but the rate of drug elimination is a first order process and is equal to K times the amount of drug in the body. And therefore, for the one compartment model, 13.5 becomes equation 13.7, which is that. And we substitute the rate of drug elimination as K times AB divided by the CP, the drug concentration in the plasma. And we know that AB is equal to CP times VD, right? So that would be K times CP times VD over CP, and therefore the clearance is equal to K times VD, or the first order rate elimination constant is clearance over VD. That's a very useful equation. Very, very useful. Now let's see how to calculate drug clearance. So here in example 13.6, calculate the clearance of an anti-cancer drug from the information that was provided in example 13.4. So 13.4 is when we plotted the data and we have determined the VD being equal to 97.6 liters and the K was equal to 0.461. You see how easy it is? That's how we calculate clearance. That's amazing, right? So the clearance is 45 liters per hour. So therefore 45 liters of plasma are cleared of drug per hour. Okay? This is nice. So finally, it's practice time. I have here 13.12 that is asking you to determine the relative distribution of a drug in a 70 kilogram male that has a volume distribution of 4.5 liters. Okay. 13.13 is asking you from the best fit equation to determine the volume distribution, and you are given the dose. Okay, and you are given the best fit equation. Here, it's a theory question that essentially you have to choose the correct statement that correctly states the definition of clearance. Okay, and at this point, I would like to thank you for your attention. Until next time.